Hello, Assalamu alaikum. Welcome to the lecture number 10 of the series of designing and implementation of RISC-V pipeline code. In today's lecture, we are just going to update our top pipeline architecture, which we have designed in our two previous back lectures. And then in the previous lecture, we have designed our hazards unit, which we are going to integrate today. And a few more signals updation we are going to be do in our top architecture. And then we are going to run some tests and see that either the hazard unit which we have designed remove our data hazards or not, or we are still facing any some errors, right? So let's go without any further delay. This is an implementation of pipeline top part 2, because definitely we are just going to update our top architecture. So before just I'm going to show you this updated pipeline top architecture here. So as you can see here that there are a few signals, they have highlighted few of the blue signals which are going to be updated in our architectures. First, we have already designed our hazard unit with following inputs and outputs. So that is done in previous lecture. What we have to do is just we have to generate few new signals. Most of the signals have already been generated. We just have to connect them to our previous, as I have shown in the previous lecture, that I have already designed 3x1 mux. So that part is also then we have just to initiate the 3x1 mux and connect it here. Same goes with the hazard unit as well. But you can see here that there are a few new signals that from the decode cycle. We have two RS1D and RS2D signals, which are getting a map of RS1 and RS2 values from the instruction format. And these are going as the output of RS1E and RS2E, which will be an input to our hazard units. Right. In the same way, the result reg write W is going as input signal. So definitely these signals I've already mentioned. So we are just going to use it as it is. But here you can see that ALU result M is just acting as one of the inputs towards the execution unit as well. But we have it is for our design in previous, it was an output. But now we are just going to use that output as one of the input as well of the mux. In the same way, here you can see that the result W was, which was not an input towards the execution stage, it was the input towards the decode stage. But here now, as we can see that the result state have W Y has been providing as an input towards the execution stage. So we have to mention that the input signal to that execution state, so we that can use it into the mux. So this is the updated architecture. So without any further delay, let's move towards the coding part. I've already made some few changes in my files. So I'm just going to quickly go through it, and then we will move towards the integration and the connection part, right? So first, let's see our decode cycle that I have mentioned that we have to provide two new signals at the output, that RS1E and RS2E. So if I just show you here that what logic I have been here, that I have defined them RS1E and RS2 as the 5-bit output ports here, right? And they are been assigned the values of RS1DR and RS2DR. RS2 is a register because definitely we have to read that instruction, and that both signals are getting the value of instruction D from 15 to 19 for RS1D and from 20 to 24 from of instruction D to RS2D. These bits are predefined in the instruction format, so definitely you can look into that. So the decoding, the signals which have to be mentioned in the decode cycle, we have already done that. We have already provide the register for that as well, and we have also mentioned them as an output signal of RS1E and RS2E. Further changes we have to do is in the execution cycle that I have mentioned. As you can see here, that I have mentioned the input signal of result W, a new signal here, because as mentioned in the previous right now that the result W is providing as an input to the execution stage. So I've already mentioned here, but I have not used it here till yet. I just mentioned it, so definitely we are going to use it into mux signal. So let's first declare our hazard units in our top architecture. I'm not doing into the hazard unit into the execution unit, definitely, because if you enhance your implementation or architecture, so definitely the more hazard you are going to face. So those logics can be implemented to hazard units. So that's why I'm initiating it into the top file rather than initiating into some of the internal states, right? So just quickly initiate our new module here, which is the, so we are declaring hazard unit here, right? So I've already opened the hazard units. We just have to copy that quickly from as input and outputs and just paste it here, right? Okay, this is an hazard unit, but I'm naming it as a forwarding. right? Because this is a forwarding block. So this name is a forwarding block, and then just quickly connect our ports with it. Definitely this is a reset port. Okay, reg write W, sorry, reg write M. Then we have reg write W. Then we have RDM. Then we have RDW. Then we have RS1E. Right. Then we have RS2E. Then we have forward A signal. Then we have forward B signal. Okay. So just quickly connecting the reset signal with the reset pin. Okay, for here reg write M we have already mentioned in the top file before, because the reg write M was an in output of the execution stage and the input towards the memory cycle. So we are just going to connect that reg write M signal here directly, because definitely it has to go towards after it is connected after the registers. We can see here that the reg write M signal is connected after the M signal, before the clock of the cycle write back memory internal register. So that's why we have just using the output signal of the execution stage as a input towards the hazard units. Similarly, that reg write W I already mentioned, as we can just quickly search it here, because it was an output of the memory cycle and was also an input towards the decode stage one of the. So definitely we are just going to use it without any registers, right? Because memory is already have been registered internally. Okay. So then we have RDM and RDW. These are also have been mentioned earlier. So just using them quickly. Okay. So for the RS1E, this should be an output signal of the decode, right? Okay. Sorry. See, so as you can see, I have already mentioned RS1E here and RS2E here, and these are the output ports of my decode cycle. So let's just add some the scope so that I'm just going to connect quickly with my hazard unit, right? So RS1E will be connected with RS1E and RS2E will be connected with here. And now I have two outputs for the forward for AE and BE. So just using it as it is right now. And I have to mention the signal in here, right? So let's make it a wire of 2-bit signals and just copy it quickly. Forward BE, comma, forward AE, right? So we have already done, but definitely these two are the outputs of the hazard unit. So these have to be provided as an input towards the execute cycle. And you can see that I have also not mentioned the result W here. So just quickly going to mention that signal as well, because it is an input and that input is coming from my write back stage, right? So write back the result W will be connected with my result W signal. Now I'm just mentioning two more signals here, that forward AE as an input and now the forward BE as an input, right? So just going to connect it quickly so that both wires get connected. So just to make sure that naming convention is a little bit different, I'm just adding a underscore here so that the signals don't get confused with each other and the values don't get corrupted. Right, so now quickly I have to add these two signals into my execution as well. So just quickly connect, copying it and mentioning it here. Okay, so forward A have been done, and here I'm just going to press it forward with BE. And these are inputs, so let's declare the input here quickly with 2 bits, control E, comma. Okay. So here we have done this the basic connection we have done, or that we have defined the two signals from the decode and output provided execution. Hazard unit been initiated. We have connected all the signals with the hazard unit and output ports. Now what we have to do in the execution state, that we have to initiate these mugs and connected it accordingly, right? So just quickly, I've already designed the mugs here, so I'm just going to copy it. Control C. Okay, make sure that here the logic maps with our, because the control signal is a little bit different here. So we have to make sure that we don't connect the wrong ports with that, right? So for just quickly going to initiate C by one mux for source A, right? So I'm going to connect it here. Let's name it at the source A mux, right? We have A here, we have B here, we have C as input, S as our control signal, and D as a output. So just keeping, we have to have to be very much, what you can say, precaution in connecting these signals. As I know that for the A, that RD1 as an input is connecting to the A. So just I'm going to connect this RD1. Okay, let's make sure that this is an input signal as well. So just going to connect it from here and let's delete it from here so that we don't get any mistakes in connection. So A is just the RD1 A, right? In mux B, I have know that B connects of the 0 1 signal, right? So whenever I have a 0 1 signal, you can see the signal is coming from my result W port, right? So I have to connect my result W port to my B port. So result W was also an input, so just connect it to the B. And in the same way, I know that ALU result M, which was an output port, is my C input, right? Here, and at forward AE will be my selection bit. And let's name it as a wire. We have already mentioned here source B, so let's mention it as the source A for now. So I'm just going to connect the source A to my output and simply connect it with my input of A. Okay, you can see here that we have only one mux and source A, so we don't have any other mux here, so we can just simply connect that wire. Now let's move towards copy pasting this mux for source B as well. Okay, so for source B, we have to very much precaution because we have two mux here. One is going to connect because one for the immediate value and the extent immediate value and for this operand or forwarding value, right? So the ABC will remain same. We are not going to change that right now because result B for its result WR result is just going to control signal from A to B, and RD1 will be converted to my RD2, right? You can see here that RD2 here I have bugs here, so I'm just smoking it. Going to make a source B interim, right? Because it shows that this is source B interim wire, so we're going to simply quickly mention it here because there are two source B signals. I don't want to mix the names. Source B interim will be my input towards my second mux, which will be let's see again that source B. I've made a new signal here, wire source B interim, which is connected to the 0 port of my mux. So what we have done, we have replaced the RD1 with the source B interim, which we have mentioned here. Right now, the next change should be here. What we have to do that previously on the right data, we have connected the RD2 directly, right? But now you can see that the source B interim is getting connected here. So first, let's check where that white data M is here. For right data M, because definitely this is an output M. So for that, we have connected the RDER signal. So let's RDER signal is getting by RD2E. So we have to replace this RD2E with our source B in time. That is very much simple here. So I'm not changing any wires name and all that. So just I'm just connecting, right? So I guess this is what have to be done. We have already implemented our mux here, connected the hazard on the top cycle, connection all the wires here. So I guess this is all from our side. Let's check, try to run a test here. First, let's see that the memory has the same instruction which we have tried to run previously. That it is two add-I instructions. Then we have a add instruction. Then we have a load add-I instruction, and then we have a add instruction, right? I'm not sure what these instructions are. So let's see how we are going to do it. Right. So just quickly, I'm going to write my I Verilog. Let's write it I Verilog minus O out dot VVP. And then we have a pipeline T. Okay. So pipeline TB. What is file pipeline underscore TB, and then we have a pipeline doctor. Okay, we have some errors here. Let's see what are these. It says that pipeline top beat 81. In pipeline top line 81, we have an error of some syntax error maybe. And why is that? Okay, we have forgot to add some comma here, right? So just quickly write it. Okay, RS1 is not a port of decoding. Okay, for decode cycle, I guess I forget RS1 is not an RS1, right? Oh, sorry. I guess these are mistakes already have underscore RS1. Okay, so just make sure that these signals are not interfacing. Okay, right. Perfect. Okay, now RDW expect 5 bits. So what then be the issue? Maybe we have forget something of the hazard 146 line. Okay, so RDW. Let's see to the hazard unit what we have provided. In hazard units, we have an RDW of 5 bits. So why it is giving me an error here? Maybe this RDW. Okay, we have RDW, not underscore W, right? So that can be one of the errors. Right, correct. Okay, so let's run it again. Okay, we have no errors here, so it means that all the syntax have been removed successfully. Now simply writes at VVP out.vvp. So dump file has been generated here. I've already opened my previous dump file. I'm just going to, okay, let's just quickly save answers here. That initially previously we are having a 5 answer on the 5th register, then 6th register have value of 3. So we are expecting that 5 plus 3 should get an answer of 8 here, but we got an X because of the data hazards. And then we have at 8, we are uploading an 0 value. So we got 0, and then for 9 we have 1. So 9 plus 1 we are expecting that to be 1 answer, right? So, but we didn't get that. So let's see this time we have got the signal or not. Okay. So just quickly, you can see that I just refresh my waveform, and you can see that all of my the X signal from the result W just quickly convert into the green, right? It's mean that our forwarding logic has been successfully implemented. Now you can see here that my answer at the 5th register has been read successfully. The 5th for the 6 is get 8. And then we know that for the 7, it should be the addition of 5 plus 3. So you can see here that I got an answer of 8, which means the 5 plus 3 has been successfully added together. Just to make sure we can add where we have the, I guess in decode cycle, we have a ALU. Oh, we must be having an ALU into our execute cycle. So just quickly goes to the execute cycle and call our source A and source B. Okay, I'm just adding these signals, and I guess what we have as a result port of ALU. For the result port, we have ALU of result E. Right, so just quickly connect it here. So here you can see that first we have 5 and 3. On both ports we have 5 and 5, right? Sorry, 0 and 5, and the answer got 5 here. Then we have 0, 3, and answer we get 3. And then after that we have 3 as it is. If you can see that the forwarding signal we have implemented here. So just I want to quickly add that. So definitely we can have an idea what has been happening here. So you can see that the forwarding signal is here is for A is 0, 1. This means that you have to get that answer from the write back stage. And for 1, 0, it shows that we have to get the signal from my memory stage, right? So the forwarding signal has been activated. This means that my data, my mux has been working and my data got bypasses. That's why I get 5 and 3 and my answer got 8. Similarly, you can see here for the next cycles that I got in 0 here, right? And then after that, okay, these are for 0. And then here we have a 1 input, because these signals are getting X because of the registers. Sorry, definitely the execution was happening here. So you can see that we got an update of the forward E signal. Let's okay get 0, 1 in from the write back stage, because at the time we are writing an 8 0 value at the load 1 instruction. So we are writing a 0 value to its memory location, and again 1 0. So we are getting the bypass from our memory stage. So we are get the bypass results, and we have just added 0 plus 1, and we get our final result of 0 plus 1. So this shows that our hazard unit have been completely implemented successfully, and we have reduced the forwarding error which we're facing in our previous implementation. Right, you can see here that we have already have a forwarding block also. So definitely just quickly going to add these signals so we get an idea. So let's say reg write M, reg write W, RDM, RDW, RS1E, RS2E. Right, so you can see here for and forward AE and forward B, right? So let's just quickly connect these and see that for reg write M, it was get activated from very time to time when we have this forward A signal here activated. So our condition was getting through that we have a reg write M, we have an RDM which is not equals to 0, and RDM was equals to RS2. That's why we have a forward A of signal of 0, 1. Similarly, you can see that right W we have 1 and we have 6, and we are getting from RS2 or RDW, and was similarly with RS1. That's why we get 0, 1 and 1 0. So definitely you can confirm this logic from your side as well individually. So this conclude our today's lecture that we have successfully implemented our updated top line architecture with hazard unit integrated in it, and we have reduced the data hazard which we were facing previously. So I hope this make all your logic very much clear and all of these issues have been solved. So maybe this can be a last video of our tutorial series. So you can try to implement more instruction in it and try to run it more code on it, and you can extend it to for further instruction, and definitely you are going to face any issues in it. So you can contact us anytime. So we will try our best to answer your queries, and if there is some topic which have been left over and we feel that this should have been covered, so definitely we are going to make a new video for that. So this conclude our tutorial series for this 5 implementation of design and implementation of pipeline architecture of RISC-V architecture, right? So thank you all for your support and being with us for during this whole series. So thank you very much. Take care. Allah Hafiz.